Let's talk unit analysis. What do I mean by unit analysis? What I mean is we're going to look at an equation and we're only going to concern ourselves with the units in that equation. And we're going to derive the final units given the equation that we have. Let me give you an example. Let's talk or talk about velocity. Now, some of these equations I'm going to put down, maybe you haven't seen before. This one I'm sure you have. But as you get deeper into this course, we'll do more and more equations, and every now and then I'll say, hey, let's stop and do a unit analysis and just figure out the units that go wrong, along with the parameter that we're trying to derive. In this case, velocity is rate of change of position. It's how fast position is changing. So we'll put displacement, delta S, in the numerator, and we'll put time in the denominator. There's a video on the kinematic parameter, but this is the equation. The units for displacement are any units of length: meters, feet, centimeters, yards, miles, kilometers, whatever we want to use. I'm going to use meters for this example. The units for time are any units of time: seconds, minutes, hours, days, months, whatever it is. For this example, I'm going to use seconds. And I just did a unit analysis by following through the units for each of the parameters in the equation, and I derived the units for velocity, which are meters per second. This could be miles per hour, could be kilometers per hour, whatever it is. But we used, in this example, meters per second. All right, that's a very simple example. Let me do another one. It's a little bit more complex. Let's do acceleration. Acceleration is the time rate of change of velocity. We use the equation A equals delta V over delta T, how fast velocity is changing. Well, we just derived the velocity units up here, that's meters per second. And if I just stay with the same time seconds as seconds, I get this funny looking equation. And again, this time could be hours, minutes, months, whatever it is. This could actually be some other velocity parameter, miles per hour, kilometer per hour, whatever it is. But for this example, I'm going to use meters per second. And I'm going to put seconds in the denominator. Well, if you remember from our fraction review, this is seconds over 1 in the denominator. And now I have our fraction divided by a fraction. And it's really multiplication. We multiply the numerator times the inverse of the denominator, or meters per second squared. And I just derived the units for acceleration. Okay. Um, and you are probably very familiar with this type of set of units, in that we often say acceleration is due to the force of gravity is equal to negative 9.8 meters per second squared. Sometimes this meter per second squared just gets sort of nebulous in terms of what it means. Well, what it means is exactly what we derived, and it means this right here. And when we get to this explanation in kinematics, you'll see this. Acceleration is nothing more than how fast velocity is changing. So it's meters per second per second. So this meters per second squared is really meters per second, and saying acceleration is negative 9.8 meters per second every second, right? So that's just a unit analysis. Let me give you another example that we'll get to in kinetics. We'll use the equation, add up all the forces acting on an object, and that equals the product of mass of the object times the acceleration of the center mass of that object, Newton's second law. Well, mass has the units of kilograms. I'm going to put that right here. And acceleration, I'm going to do unit analysis. I'm only going to put the units of acceleration in here. They get meters per second squared. Or we could just rewrite this as kilogram meters per second squared. Well, that's good. That is, in essence, what the units of a force are. But the force is often just referred to as a Newton or N, and that's fine. This is a special case where some units together are called a special name. In this case, that special name is a Newton. Well, 1 Newton is the force necessary to accelerate a mass of 1 kilogram, 1 meter per second squared. These are the base units of a Newton. And sometimes we actually need to know that as we go forward. So for example, let's go to another equation. Torque there's two equations for this, but I'm going to use this one right here. Torque is equal to the force times its moment arm. There'll be lectures on this because this is really important to understand. But in this case, let's just do a unit analysis. We have force units, which are newtons, times d, which is a moment arm, and that has units of length, and units of length will be meters. Well, there's our units for torque. Now, if we want to derive this out a little bit further and to continue with a unit analysis, we could put the units of newtons in there as a kilogram meter per second squared times meters. And if I put that 1 in the denominator, now I get another set of units, kilogram meters squared divided by second squared. We may actually find it useful at some point to use these set of units versus a Newton meter. They mean exactly the same thing. They're exactly the same thing. They're equal to each other. But through a unit analysis, we can discover what the base units are of a particular parameter. So again, a unit analysis, we're only concerning ourselves with the units and the parameter. We're not concerning ourselves with the magnitude of the parameter in the equation. And it's a good way to make sure that the parameter that we're trying to derive, that we understand the units that we ultimately get out of that equation. Okay, thanks.